Okay, here we are on lesson 6.6. We have a visitor today, Faris. Is that how you say that? Yeah. So we'll welcome him in. You're going to be on our YouTube video now. Yeah, so a little shout out. Anyhow, so yesterday we learned how to essentially factor polynomials that are higher degree using synthetic division and the rational root theorem and a little help of the graphing calculator. So we'll do that again today, and then we also are going to work backwards a little bit and go from if you have a root or if you have some given zeros, could you write a function? So my first question will be, if you have a given zero of -2, what would be the corresponding factor where that 0 would come from? Okay, okay, how about I'll be a little more specific. What linear binomial factor would -2, a 0 of -2 come from? If you were working your way backwards through from the answer to the polynomial. No. Okay, watch this. I bet you if I write this, you'll have a better idea. What linear binomial factor? X plus 2, good, yeah, there we go. Now you're starting to think backwards a little bit. So if x plus 2 is a factor, then -2 would make that 0, thus being a 0 of the polynomial, right? What would correspond with 2? X minus 2, good. And now you're catching on x minus 4. Right, so this would be, if we multiply these factors out, that would give me a polynomial, the simplest polynomial, with those zeros, right? It's not the only one, but it is one. So let's just take a little time and practice multiplying these linear binomials. Okay, so how would I multiply these two together? What would I do? Because I'm multiplying three things, so I multiply two at a time. Foil, right? Which I don't like foil. You ever heard of foil?
Not really.
Yeah, it's foil is this thing where they say, okay, it's an acronym, FOIL. It's kind of dumb, but it's a little acronym to remember how to multiply two binomials. So like they say firsts. You can't see this on the video because I'm pointing with my fingers. So like first terms, right? That's x squared. Outside terms, that's going to be -2x. I for inside terms, that's positive 2x. And then L for last terms, that's -4. I don't know why. But it only works for when you do a binomial times a binomial. That's why I think it's dumb. So I just like to say double distribute instead. So it's take x times those two and take 2 times those two. Right? You get the same thing. So multiply those out. You end up with x squared minus 4. Okay, and then we have to multiply that by the remaining x minus 4 to get our polynomial in standard form. And so we essentially have to double distribute again. So double distribute, take the x squared times both of those and the -4 times both of those. And you'll have your polynomial that would correspond with those zeros. So we'd get x cubed. X squared times x is x cubed. X squared times -4 is -4x squared. Distribute the -4 here. We get -4 times x is -4x. And -4 times -4 is plus 16. So right here, this would be a polynomial, the simplest polynomial that would correspond with the zeros -2, 2, and 4. Right? And if you look at this polynomial now and you start thinking because we just work backwards from what we're used to doing. But if you look at that polynomial and you think, how am I going to factor that? Okay, well, look at it. This one actually has 4 terms, and I think it would factor by grouping, don't you think? And if you grouped it, it would factor, and you'd get what you have above, and then you could go difference of squares, and so we're just working backwards now. Okay. This next one, when we have 0 as a factor, this one kind of throws people off. Or 0 as a root, excuse me, what factor corresponds with 0? See, I think it bugs people because it's not like x plus or x minus something. It's just, no one ever writes minus 0, do they? Just x. So, you know, nobody ever really writes minus 0 ever. You know, like, who's your favorite basketball player? Like, you got a favorite guy?
Chris Paul.
What's his number?
3.
It's not 3 plus 0 on his jersey, is it?
No.
That would be weird, wouldn't it? 0, yeah, double 0. I don't think you can have double 0 in hockey. I like hockey. So, but I don't think you can even have 0. I've never seen that number. So x would be a corresponding factor, right? For 0. What about 2/3? X minus 2/3. Good. You know, you're going to get fractions in there. You could also, if you wanted to not deal with fractions, you could say, what, 3x plus 2? Or, excuse me, minus 2? Right? But that would not be, I guess, simplest, because you would have an extra factor of 3 in there. But no big deal. I'd almost rather have that than to have to multiply the fractions, because they're so dreadful. Yep. And then if you had 3 was a root, then x minus 3 was a factor, and then you could multiply all that out, right? Do you want to multiply it out? Yeah, sure, it'd be good practice. Let's do the one without the fraction though, huh? So x times 3x minus 2 would be 3x squared minus 2x, and then multiply that by the remaining x minus 3, and you'd be left with 3x cubed minus 9x squared minus 2x squared plus 6x. Combine your like terms and you end up with 3x squared minus 11, cubed. That's a funny 3. X squared plus 6x. And that's a 3 right there. So what do you think about that? Any problems there? Do the professors at Carleton use smartboards? Or do they just use old school chalkboards? Actual chalk? Yeah, I knew it. I knew it. When I student taught in Australia, and that's what I had. Just a chalkboard. One would slide up, and then you'd have the one behind it, you know? Yeah, that's it. I had to rewrite everything in chalk if I wanted to do it. No, they don't have Zambonis, and actually they do. All right, we're wasting time. So now, fundamental theorem of algebra. If we want to read the mathematical definition here, and then we can maybe paraphrase. Every polynomial function of degree n greater than or equal to 1. So it's good for you to read the math book, parts of the math book. I know you probably don't ever do that, but at some point if you leave the friendly confines of Northfield High School, you might have some professor someday that just says, here, read this, do these problems, and you know they expect you to be a little more do this on your own. So it's good for you to read this every once in a while. Every polynomial function of degree n greater than 1. So hopefully you understand what that means. Has at least one 0 where a 0 may be a complex number. So now when we start talking about complex numbers, we open it up to the possibility of having an I in there, right? Which stands for the imaginary unit, which corresponds to the square root of a negative value. So now we're going to introduce the possibility of having imaginary roots. Okay, so there's a corollary. Every polynomial function of degree n greater than or equal to 1 has exactly n zeros, including multiplicities. So I guess in simpler terms, whatever the degree is, that's how many roots you're going to have. So if it's fourth degree, you're going to have 4 roots. It's just that some of them might not be real. They might be complex roots that contain imaginary units. All right? This example over here to the right just highlights a scenario where that would be the case. So if you have x to the fourth, blah, 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 and here's all of the possible rational roots using the rational root theorem. And you can see they use a little technology so that it's not all guess and check. And they start using synthetic division to factor that. And what happens on this one is when you get down to it, you end up with x squared plus 4 is one of your factors. And that does not have any real zeros, because you can't square something and make it negative. So x squared plus 4 will never be equal to 0 unless you have an I, right? So that's where the solutions x equals plus or minus 2i come from. And the complex conjugate root theorem basically states that if you have an imaginary complex root, then they will come in conjugate pairs, right? They always come in pairs because you take plus or minus, and they always come in pairs. Okay? So pop over to the next page and we'll do one of these all together from start to finish. And then that'll pretty much wrap it up. So we have a fourth degree polynomial with 5 terms. How are we going to factor this and solve it? How are we going to solve this? Are we going to unfoil it? Yes. Oh, it's 3 terms. Are we going to, is it the difference of squares? No. Okay, so it's got 5 terms. So this is where we're going to use our rational root theorem and our synthetic division. Yesterday we learned about the rational root theorem and all the possible roots that there may be. So plus or minus p over q, where p was the constant term and q is the leading coefficient. So that gives me possible rational roots of plus or minus 1, 2, 4, 5, 10, or 20, all over leading coefficient of 1. So that doesn't give me any fraction possibilities. But still, that's plus or minus 6 times 2, which is 12 different possible roots. So if we're going to just use guess and check, and we are the unluckiest person in here, it could have taken you 12 tries, well, maybe 11 actually. Depends on how many real roots there are, or rational roots there are, but it could take you a long time. So I plug this into my graphing calculator to get a peek at the graph, and I can factor it that way. So I plug it in there, and what I notice is that this polynomial seems to cross at 1 and negative 5. So we're going to confirm that those are actual roots using synthetic division. So I'm going to try 1. I'll just put 1. It doesn't matter which one you put in there, but I'm going to put 1 in there first. So I'll use synthetic division and see if 1 gives me a remainder of 0, which ultimately I'm checking if x minus 1 divides evenly, correct? Okay. So my coefficients of that polynomial are 1, 4, negative 1, 16, and negative 20. Bring the first one down. 1 times 1 is 1. Add them, you get 5. 1 times 5 is 5. Add those, you get 4. 4, 20. Ta-da! Remainder of 0, so it divides evenly. So that's confirmed to be a 0, and x minus 1 is a factor. So we have constant, linear term, quadratic term, cubic term. Right? So essentially I'm factoring it, right? I've just factored it into x minus 1 times whatever my quotient was. Yeah.
What's the point of putting P over Q if you can just like look at the factors of 20 and then since the first one's a 1, you just like look at the factors of 20 and guess those? Like
Are you more or less asking what's the point of doing that part?
yeah.
Well, if this was like a 2, then this would be plus or minus 1 or 2.
So then you would have
And then you would have fractions. Like,
oh
really the only fraction you would have is 5/2. So would add that as a possible rational root.
yeah.
So yeah. Okay. All right, so now I also determined on the graph that 5 was a likely candidate for a rational root. Sorry, -5. So I'm going to take the quotient stuff. So I'm going to take this stuff and I'm going to divide that now. So I don't divide the original, I take that stuff. 1, 5, 4, and 20. And I just go again. 1, -5, 0, 0, 4. Ta-da! Found another one. Constant, linear, quadratic. So now, after I've done synthetic division a couple times, I've got this down to be a quadratic function. That's my remaining factor. So what I essentially just did is I factored x minus 1, determined that was a factor, determined that x plus 5 is a factor, right? Because when I put -5 in and run that in synthetic division, I'm checking to see if x plus 5 divides evenly. And then my remaining stuff was x squared plus 4, which is very similar to the problem that we just looked at, that example. Maybe it was the example. I don't even know. Was it the example? Nope. So what are the zeros then? Okay, well we have 1, we have -5, and here we have 2i.
oh wait, nice.
Yeah, that's good. 2i,
Wait,
but they always come in conjugate pairs, so it's plus or minus 2i. Okay, and some of you might be thinking, well, how did you just come up with that? Well, we're really asking ourselves because we're using the zero product property, so really all of this stuff we are making an equation, and it was like, when is it equal 0? Right? So when any one of those individual factors is 0, the whole equation will be true. And so when is x squared plus 4 equals 0? We have like a little mini equation to solve there. Well, you can get x squared by itself, and x squared is equal to -4, and then you can square root both sides. And when you do that, you're going to get plus or minus the square root of -4, which is plus or minus 2i, right? So there's your 4 solutions, your 4 roots. It was a 4th degree equation, so there should be 4 zeros, and 2 of them in this case are complex with imaginary parts, right? 0 plus or minus 2i. So they actually don't show up on the graph as crossing the x-axis. All right. There's a couple things I want to talk about that I've seen today, common mistakes. The first one is when you have a situation, whoops. -2, whatever. Okay, so when you have a situation where you're multiplying a couple binomials like this, I see this all the time. Students will just look at that and go, oh, that's just x squared plus 1. Like I don't know, it's like a hyper simple, oh, I know, I just square that and we're good to go. No, that's not x squared plus 1. You gotta double distribute it out. So what it's supposed to be is x squared plus 2x plus 1. So I think sometimes people will just come up with their own simple conclusions and just kind of forget about. That's why, I like to write stuff out and show your work and be very thorough. Okay, so don't make that mistake. And then, gosh, there was one other mistake there's one other thing. Let me think here for a second. Okay, kudos to Dylan Dietz, even though he's a Bears fan. And oh, sorry about that field goal, bud. Oh, I forgot to talk to you about that. Now you know how it feels. Anyhow, he reminded me of what I wanted to share with you. There's a question on the homework. It's not like that, though. It's like, if you have x to the fourth minus 81, let's say we have this, okay, and you want to factor that. Doesn't that look kind of like the difference of squares? But it's to the fourth power. But could you still use the strategy, that identity that every difference of squares factors by? And you could make this, because x to the fourth is a perfect square, it's x squared, right? So this right here is kind of like a difference of squares within a difference of squares, see? It's kind of neat. So you might need to be able to use a little creativity with some of what you know about factoring. Kind of like these type of factorings. X squared. Let's say we got x squared plus, let me make one up, 7, or x to the fourth plus 7x squared. Oh, I don't know. Minus, let's see, what would be two factors that have, or factors have a difference of 7? 18, let's go. Just like this, can this unfoil? Can you factor this trinomial with unfoil? Yeah, sure, you could. This would be x squared and x squared. This would be plus 9 and minus 2. Right? Just like that one. So some of those higher degree polynomials, you can still use some of the strategies that we learned for like lower degree, like quadratics, the stuff we use in the quadratic unit. So there we go. All right, that's going to wrap it up.